We now introduce our model of the renewable resource. We focus on the fishing industry, but the model, of course, applies to any renewable resource, such as, for instance, forests that grow naturally and logging, pastures, or the hunting of endangered species. The model is in discrete times. We write the stock of fish at time t, st. St here is the state variable of the system. Without fishing, we say that the stock would reach a maximum that we call the carrying capacity of the ecosystem, and we write the letter K for it. So of course, if it's a small ecosystem like a lake, then K is not too big. And if it's a large ecosystem like an ocean, then the K is much larger. So why this K? Well, simply because fishes, like any natural species, cannot grow infinitely because at some point they either run out of food or they get too numerous and they get other species to eat them. So they can't, at some point, there's a limit to nature's ability to sustain a large population. The natural growth of the stock of fish is logistic. So we write tau of st equals to r st that multiplies 1 minus st divided by k. So here r is between 0 and 2, and it determines how fast a species can reproduce. To see what's going on, note that st actually enters the function in two places. So the first st reflects the fact that you need parent fishes to get baby fishes. And so to have more fish, the more fishes you have, the faster the population will grow. But of course, there's another s within the parenthesis that actually reflects the retraction from the environment. So as we get close to the carrying capacity K, then even with lots of offspring, then the population cannot grow more. And so we'll eventually stabilize at K. Then there's R. So R, of course, if it's close to 0, it means that the species will reproduce very slowly. So examples would be something like trees in a harsh climate, or maybe large fishes or large sea mammal like whales that take a very long time to reach maturity and reproduce. On the contrary, then a large R would represent some species that reproduce quickly, like sardines in the sea or rabbits, for instance. Then you may ask yourself, why is R limited at 2? Well, it could be above 2. The problem is that if it's above 2, the species reproduce so fast that eventually you get steady states that don't have a single value. To convince yourself of that, you can just try with postulating some value for k and for r that is maybe like 3. And you can just take your calculator and see what happens. You will see that you get all kinds of weird things going on. Actually, for the nerds among you, I highly recommend that you look that up. So search for the logistic map and the Feigenbaum constant. You will not regret it, I assure you. So just to see whether you understand, are there any steady states in this model or not? And if yes, how many? Think for a while. So, well, we have two steady states. To find them, you can just write the equation essentially. So imagine that the steady state S is S star. So you just write R S star that multiplies 1 minus S star over K equals to 0. And then we ask ourselves, are there solutions for this equation? Of course, we have two. S star equals 0 and S star equals K. So if S star equals 0, it means that if you just don't have spontaneous creation, if you don't have parent fishes, and even better, one dad fish and one mother fish, then you don't have other fishes. But as soon as you actually, as you have epsilon quantity of stock, then it's good enough, and the population is going to reproduce. And of course, if you get to a population of k, then it can't grow further, and so it's going to get stuck at k with the growth of 0. All right, so now we see graphically what this logistic growth looks like. Here's the representation of the logistic growth. On the x-axis, we have ST, and on the y-axis, we have the growth of ST, so the growth of the stock of fish, which is, of course, tau of ST. And as we already said, so the growth of ST is equal to 0 when ST is equal to 0 and ST is equal to K. And it would be quite easy to actually compute the maximum value of the growth of ST, and I think it would be something like K over 2 if we did compute it. So of course that's the maximum, the point at which the species grows the fastest, which is just halfway between the fact that here we have too few individuals and here we are too close to the carrying capacity. One question that we can ask, and I will let you think about it, is what steady states are stable or not stable in this system? By stable, I mean that if, so S is at the steady state, but we have a small deviation from S, then the system will naturally go back to this same steady state. Whereas if it's unstable, then as soon as we move a little from there, then the system escapes from that steady state and goes to some other steady state. So think about it for yourself. I'm not giving you the answer. Let's now turn to the fishing industry. We assume that renting a fishing boat costs C to a fisherman or a fisherwoman. Here, think of C as including also foregone income from any other activity that that person could do. So it really is an opportunity cost, and it's going to be just an exogenous parameter. Each boat catches a small fraction, alpha, of the total fish stock S. Alpha is also exogenous, and it depends on the available technology. So we can imagine that traditional fishing had a small alpha, while modern trawler or fishing boats with GPS and fish finders have a high alpha. The number of boats rented is B. Here B will be determined endogenously by the model. So if fishing is lucrative, then lots of people will want to rent fishing boats. But if it's not, then fewer fishing boats will be rented. The market price for a fish is P. So just to see if you are following what type of demand this is, how elastic is this demand? This demand is perfectly elastic. The price P is what the fisherman can obtain for a fish, and if that fisherman asks for a higher price, then nobody will want to buy it. So to make sense of this, just think that it's a small fishing community that sells to the international market. The goal here is to just be able to not think too much about consumers or consumer surplus and focus on the fishing industry. Of course, consumer surplus does matter. So the thing is, we just want to focus on the dynamic of the fish stock, but obviously how the fishing industry goes will impact also the surplus from buying fishes for consumers. The profit for the fishing boat is pi of S, which is simply P, the sales price, multiplied by the catches, so alpha S, and minus the cost C. The total catches of fishes will be noted as harvest, capital H, and they will simply be equal to alpha B S. So alpha S is the number of fishes that one fishing boat catches, and B is the number of fishing boats. Then for the model to be interesting, we need one assumption. If S equals K, then fishing is profitable for a fisherman. This means that pi of K has to be greater than 0, or P alpha K minus C has to be greater than 0. Why do we need this? Well, simply because if not, then nobody would just want to rent a boat and fish. So it has to be at least profitable for the first fisherman who has the whole ocean to fish to be able to make a profit. Otherwise, nobody would. So we have the natural growth rate and the catches that allows us to find the net growth rate of the stock of fish. So it's in discrete times, so we'll write it delta st, which is equal to, well, how many new fish would enter the ocean without fishing. So that's tau of st minus how many fishes are caught. So that's harvest at time t. And now we just substitute what we know about these two. So it's delta st equals to, so it's rst times 1 minus st divided by k minus, and now this is alpha b. And both is not a constant, it's some state variable that's going to be described by the model. So it's going to change over time. So we have to add both at time t and stock at time t. So the interpretation of this harvesting function is quite intuitive. So of course it's proportional to how many boats are trying to catch fishes. But also, why is it proportional to st and not just a constant, for instance? Well, it simply reflects something quite intuitive, is that if the sea is full of fish, then it takes very little effort to catch all the fishes you want in your boat. Whereas if the sea is almost empty, then of course it's going to take a while to fill up your boat. So last piece of the puzzle we now do is find out what is the steady state. Definition of the steady state: when nothing moves. So here B does not have to move, but of course also S does not have to move. So delta S must be stable. So we write it this way. So delta S, and then it's star because that's the change at the steady state, is of course by definition 0. So now we can just substitute what we have here. So I can just write that this part has to be equal to that part. So Rs star times 1 minus S star K has to be equal, so this is the natural growth rate, has to be equal to alpha B star S star, the harvesting. And what's neat here is we get a nice cancellation because the number of fish in the ocean determines how many new fish are born every year, and the number of fish in the ocean determines the number of catches. So we can simply divide one by the other. So if I want to simplify this, I get the following. So I can divide by S star on each side. Now I get only one S star here. So that's what I'm after. But of course, it's going to be an implicit function because B star is still there. We're going to have to look at what happens in the industry to know how the number of boats is going to change. But now what I can do is, now let's just divide by R on each side, multiply by -1, And then I can add 1 on each side. So 1, and then this one disappears. And then let's just multiply by k everywhere. So, okay. So here I get S star, the steady state stock of fish, that has to be equal to k times 1 minus alpha beta star divided by r. Well, actually, what we can say basically is that S star is not determined totally. It's a function of B star, so we could even write S star of B star. But of course, our goal is to solve the whole problem. And how do we interpret this? Well, it has some intuitive interpretations. So, well, you can think about it in your head for a few seconds. So, how does is star? Well, first of all, how is S related to B? Well, it's an inverse relation because there's a minus there. So, the more boats are trying to fish, then the lower the stock of fish in the steady state will be. The higher the steady state quantity K, the carrying capacity is, the higher S is going to be. Alpha, it's the efficiency of fishing. So if each boat catches a lot of fish, then again the steady state number of fish is going to be lower. And finally, R is the how quick the fishes reproduce, and there's a minus, but it's divided there. So the two of them makes for a positive function. So of course, the more fishes are able to reproduce quickly, like if there are sardines, I don't know, then still even if there's a lot of fishing, then we're going to have a higher quantity of steady state fishes in the ocean.